Hello, in this video we're going to look at the Nobel Prize in Physics for the year 1906, awarded to Joseph J. Thomson for his theoretical and experimental investigations on the conduction of electricity by gases. Here you see one of the cathode ray tubes used. Here you have the cathode, it's a minus. Negative particles are coming from here and they can be deflected by an electrical field. Here you have the end of the tube. And when the particles hit that, you see a light phenomenon. You see a real tube that was used probably in a museum, and this is a modern version of it. Here you see the light. In that case, it's violet, but the light that Thomson got was more green-like. Okay, we go to his lecture and summarized by me, and we start with the intro. We, that's of course Thomson and his collaborators, investigated negatively charged particles with much smaller mass than an atom. We now know they are electrons. These particles were discovered using an almost vacuum tube through which a discharge was passing, leading to a green phosphorescent light. The light is caused by something coming out of the negative cathode. Crookes observed this first. He put a microcross in the path of the particles, resulting in a shadow, showing that the particles move in a straight line. English physicists saw the rays as negative electrified particles, while German physicists saw it as a kind of ephemeral waves. An argument in favor of the rays being negative particles is that they are deflected by a magnet, which is not possible by light rays. Another argument for the cathode rays being negative particles is that when they are caught in a metal vessel, they lose their charge, which was discovered by Perrin, who also received the Nobel Prize a few years later. Electric deflection of rays. The electrically charged particles can be made to change direction by both a magnetic field and by an electric field, something which earlier experiments did not show. Because cathode rays make the gas they travel through a conductor of electricity, the gas then shields the rays from outside influence. By exhausting the tubes further, there's more gas removed, coming closer to a vacuum, Thomson got rid of the shielding and the rays behaved like negative particles being deflected by an electric field or a magnetic field. Hertz, here, showed that the particles could penetrate sheets of metal, inconsistent with the idea of them being particles. Thomson investigated this further. The principle of the method used is as follows. When a particle carrying a charge E is moving with a velocity v across lines of force in a magnetic field, placed so that the lines of magnetic force are at right angles to the motion of the particles, then if H is the magnetic force, the moving particles will be acted upon by a force equal to H times E times V. This force acts in a direction which is at right angle to the magnetic force and to the direction of the motion of the particles. Okay, V is the velocity. That's also here. If also we have an electric field of force X, the cathode ray will be acted upon by a force X times E. If the electrical and magnetic fields are arranged so that they oppose each other, then when the electric force H times E times V due to the magnetic field is adjusted to balance the force due to the electric field X times E, the green patch of phosphorescence due to the cathode rays striking at the end of the tube will be undisturbed. They cancel each other out. And we have H times E times V is X times E, which you can rewrite as V, velocity, is X divided by H, dus electrical force divided by magnetic force. Then determination of the electric charge divided by mass. An electric field acceleration of particles is X times E divided by m, and T is L divided by v. That is time, is the space distance traveled divided by the velocity. The displacement of the path is d is a half times x times E divided by M times L squared divided by V squared. We can write this as E divided by M is 2 times D divided by X times V squared divided by L squared. Yeah, you can do the math yourself if you want. Or you can ignore it and accept it. We get the same ratio E divided by M for all particles, unless it is near the speed of light. Changing the used gas and or the electrodes makes no difference. This constant value, when you measure the ratio E, the electrical charge, divided by M, the mass, in the CGS system of magnetic units is equal about 1.7 times 10 to the power of 7. The ratio E divided by M is unlike any system we know. The highest known value was 10 to the 4th power. The volume E divided by M for cathode rays is 1700 times that for a charged hydrogen atom, which had this 10 to the 4th power. The 1700 times 10 to the 4th power for cathode rays. Thus the mass of cathode rays is very small or the charge is very big. The charge of the cathode is the same as that of hydrogen, thus the mass of the cathode ray particle is 1/1700 of that of the hydrogen atom. Then corpuscles very widely distributed. The particle which is present in cathode rays is present in other situations as well. Metals that are heated produce these particles. Alkali metals that are exposed to light do the same. The same is true for radioactive substances like radium and uranium. Again, we now know they are electrons, but it wasn't known at that time. Magnitude of the electric charge carried by the corpuscle. The corpuscle, or the particle, is widely distributed, but the E divided by M ratio value is constant. They are everywhere and very probably one of the bricks that build up the atom. We can measure E, the electric charge. C.G.R. Wilson, also a Nobel Prize winner later, discovered that a charged particle around which vapor condenses, that's a charged particle moving through a vapor, condenses that vapor. Is a word fallen away. In dust-free air, vapor does not condense even when it's very cold to a certain temperature. Then it does. We get supersaturation. Charged particles thus can be the center of cloud forming, which makes it possible to see the particle. Thomson described the experiment with conditions as given above. A little radium is added to bring the glass in a conducting state. Two insulated plates are electrically charged. Then the plates are dragged out to reduce the number of charged particles. When a charged particle goes through the cloud, it makes drops fall, all of the same size. The number of particles that pass is the total volume of drops divided through the volume of one drop. From the rate at which the drops slowly fall, we can determine their size. Due to the viscosity and friction, the drops soon reach a uniform speed, and the smaller the drop, the slower that speed is. Stokes gave for this a formula. V is 2 divided by 9 times G times A squared divided by mu. Mu says V is the speed, G is the acceleration due to gravity, mu is the viscosity of the fluid. If we substitute the values for G and mu, we get V, the velocity, is 1.28 times 10 to the 6th power times A squared. Hence, if we measure V, we can determine A, and A is the radius of the job and thus its volume. If you know the radius of a job, if you know it's a sphere, you can determine its volume. We can also find the number of the job, the number of charged particles, and the charge of the particle. H.A. Wilson has since used a simpler method, which is not explained here. C.G.R. Wilson showed that the drops of water condense more easily on negatively than on positively electrified ones. By adjusting the expansion, it is possible to get drops of water around the negative particles and not around the positive. Then all the drops must be negatively electrified. The size of the drops and their weight can be determined by measuring the speed at which they fall. Above the drops we hold a positive electric body, then since the drops are negatively electrified, they will be attracted towards the positive electricity, and thus the downward force on the drops will be diminished, and they will not fall so rapidly as they did when they were free from the electrical attraction. If we adjust the electrical attraction so that the upward force on each drop is equal to the weight of the drops will not fall at all, but remain suspended between the plates at their place. Then we know that the upward force on each drop is equal to the weight of the drop, which we already determined by measuring the rate of the fall when the drop was not exposed to any electrical force. That was previous. If x is the electrical force and E is the charge of the drop and W is its weight, we have, when there is equilibrium, x times E is W. X can be measured, W is known, so we can determine E, the charge of the drop. The value of that E, the charge of the drop, is found to be 3.0 times 10 to the power minus 10 electrostatic units, or 10 to the power minus 20 electromagnetic units. The value is the same as that of the charge carried by a hydrogen atom in the electrolysis of this dilute solutions, an approximate value of which has been long known. But that's positive charge of the hydrogen atom. And the other, which we are dealing here, is a negative one. It might be objected that the charge measured is the charge of a collection of molecules of the gas and not the charge of the corpuscle, of the particle. This objection does not apply to any other form in which I tried the experiment, where the charges on the corpuscles were got not by exposing the gas to the effects of radium, but by allowing ultraviolet light to fall on a metal plate in contact with the gas. The electrification, which is entirely negative, escapes from the metal in the form of corpuscles, particles. When a gas is present, the corpuscle strikes against the molecules of the gas and stick to them. Thus, though it is the molecules which are charged, the charge on a molecule is equal to the charge on a corpuscle, on a particle. And when we determine the charge on the molecules by the methods I have just described, we determine the charge carried by the corpuscle. The value of the charge, when electrification is the same as above, we have seen that for the corpuscle, the E divided by M ratio is 1.7 times 10 to the power of 7. And if E is a charge carried by an atom of hydrogen in the electrolysis of dilute solution, and M is the mass of the hydrogen atom, then E divided by M is 10 to the power of 4. We just saw that earlier. Hence, E divided by M is 1700 E divided by M. We've already stated that the value of E found by the preceding method agrees well with the values of E, which has long been approximately known. Thomson has used a method in which the value of E divided by E is directly measured and has shown in this way also that E equal to E, that the E equals to E. We must not forget that all this is entirely different for positive electricity. Thus, this is strictly about what we now call electrons. Well, this is a summary. The complete lecture can be found here. You can follow the link in the description under the video. You see another of the things Thomson did. This is the principle of a mass spectrometer, which is here further developed. This is all from Wikipedia, so if you want to follow that, follow the link. Well, this is it for the moment. Next week we will go to the Nobel Prize in Physics for the year 1907. For now, thank you for watching and maybe see you next time.